Hello, so it's 2 minutes to 7 p.m. So I'll wait for a few more minutes to see if anyone joins this call, and then I'll get started with the week 3 problem solving session. Hi Vijay, so I'll wait for a few more minutes and to see if anyone joins, then I'll get started with today's content. Okay, so it's 7:05 already, so I'll get started with today's session. So, hello everyone, welcome to this week 3 session on traffic engineering. So, I hope more people will join in as we go along. So, what I'll do, I'll share my screen and turn off my video, and then we'll get started with the discussions of this today's contents. Yeah, sure, go ahead. Yeah, yeah, sure. Sure. I plan to discuss all the topics that have been discussed in this session first briefly, and then I'll move on to solving the assignment problems. Yeah. Okay, I'll share my screen. Okay, so let's get started with today's content. So, hope my screen is visible. So, to give you an overview of the topics that have been covered in this week 3 session, week 3 classes, first is the qualitative analysis of shockwaves. So, there are two things that have been mainly discussed in this session. So, it's the shockwaves, and the other is queuing. And qualitative and quantitative analysis both have been discussed. One is related to the concepts, other is related to the more of mathematical standpoint and analysis related to that. So we'll see some of those in today's session. Then what you shockwave propagation have been discussed as well. Then after that, it's mainly about the queuing theory. I think someone joined. I'll admit the person. Okay. So next is queuing analysis. So, and it can be both deterministic and stochastic. I know the stochastic version is not discussed in detail, and those things probably are not required in detail to know, but just an overview it's required for those topics. So let me get started with shock waves. So first we looked at this kind of a picture which kind of explains what a shockwave is. So what happens here is that there is a stream of high speed vehicles that are moving behind a stream of slow moving vehicles, and what happen what will happen after a certain point of time is that this high speed vehicles will catch up to the slow moving vehicles, and once that happen there are some state, so this slow moving vehicles are in one state and this is in another state, and once it catches up to the first traffic stream, a boundary will be created, and that kind of demarcates some of the time space properties of these two different space, and this boundary that will be created is called as a shock wave. So if I have to write maybe in short sentence briefly about shock waves, so it will be, okay, let me increase the font size. So shockwaves is nothing but a boundary that demarcates the time-space domain of one flow state from another. So this has been discussed in the class already, and I think it's this is very basic concept that you should be able to understand. And there are some examples that have been also given, like at a signalized intersection, if there are fast moving vehicles that approach a queue, then queue behind those stopped vehicles, then multiple shock waves will be created, and that we will see in the next slide, where we'll be explaining about that example that have been discussed in the class. So this is about the signalized intersections. And your first assignment problem, I think, is also related to this figure only. So what happens is that, so here at a signalized intersection you can have some green time, and then your signal will turn red and it will remain red for a while, and then again it will become green and so on. And so in the x-axis this is time is plotted, and in the y-axis distance is plotted. There are multiple vehicles that are approaching that signalized intersection, and before it turns red those vehicles can pass through that intersection without any stopping. But once the signal turns red, this first vehicle at this red point, when the red this time begins, it has to stop there, and then behind that vehicle all the other vehicles will be stopped as well, and they will form a queue. So that's why there is this boundary, or whatever you call this line, that have been generated, which tells you these are all the vehicle trajectories, this parallel lines that have been shown here, and this parallel line kind of denotes that these vehicles are moving with the same speed, and once it comes to a stop, so this is the boundary that have been formed, and then after some time the signal will again turn green, and then the vehicles that approach after this point of time, like once this effect goes away, then they can pass as it is, as the traffic state were before the signal turned red. So this traffic state A is similar in all these portions, and I'll talk about what this B is. And then what happens is that once this becomes green again, this queued up vehicles will slowly start to move from that intersection, and there is some reaction time, some lost time that is associated with it, and that's why the speed and everything is changed now, and that's why you see a different slope of this line, and a different traffic state is created in this portion. Now at this point of time, when the signal is red, there won't be any vehicles upstream, sorry, they will call it as downstream of this portion. So this is further from that signal, so here there won't be any vehicles, and also in the downstream side or sorry, the upstream side where this B state is. Yeah, does anyone have a question? You can ask. Yeah, upstream is this one, D, and downstream is B. Oh, sorry. Let me just quickly check. I think here it's defined as, sorry, downstream is D and upstream is B. Sorry. Yeah. That's the way it has been defined in the, I think, lectures. So this portion, this D is uh, downstream of that signal, and this is upstream of that signal, this B portion. Okay, let me see if someone needs to join. Okay, so in this case, now how many shockwaves are created? So that's, I think, your first assignment question. So let me write it down. Yeah, how many? So the answer is 6. Now, what are these shockwaves? If I ask you, how many, first let's answer this, how many traffic states are here that are present? And from the figure, you can notice that there are 4 traffic states. One is A, which is before the signal was red and all these vehicles were moving at the same speed and passing through that intersection, and that uh, A traffic state were also prevalent in the upstream of those signal, and also after this signal again turned green, those vehicles were also having the same traffic state. Then there were another traffic state that was created, which is this, in this triangular portion, which is B, where there weren't any vehicle that were present. So here the number of vehicle that was present were 0. And then so this is upstream of this signal where it was turned red, and in the downstream also there weren't any vehicle that were present, and this is traffic state D. And finally another traffic state was created, which is traffic state C, which is after the signal were turned green and the queued up vehicles were getting cleared. So 4 traffic states, and within each pair of those traffic states you can have a boundary, and that's why out of 4, if you like those, I think 4C2 also, no, that doesn't, okay, let me check. Yeah, yeah, from 4 you choose 2, so I think you get 6 pairs of combinations. So yeah, correct, 4C2 also gives you 6. So that way you can also calculate. So if I give you the number of traffic states in general, in theory you can come up with the number of shockwaves. Now to understand this shockwaves better, between A and B, this traffic state, there will be a boundary which is shown here. Here also the traffic state is A, here is C, so there is another boundary between A and C. This is between B and C. Then this horizontal line is between B and D. Another you have between A and D, and finally you have something between C and D as well. So that's how you get 6 shockwaves. Now this floor states I have already defined. This shockwaves, this 6 shockwaves that have been created, you can classify them. So does anyone remember? Suppose I ask you, next is, so this is types of shockwave. So suppose between B and D, what kind of shockwave is created? So if you notice here, between B and D, this is the stop line, and this is a horizontal line that you are getting between this B and D. So the boundary is like that. So that's why it is called as a stationary shockwave, and this is generally called as a frontal stationary shockwave. Then between flow state, suppose I pick, let me quickly check. So B and A is fine. So here the stationary, as I have mentioned, means that location of that shock wave is fixed. So this is the stop line, and frontal refers the formation of the shock wave at the downstream. So this they call as downstream, or the front end or the front edge of the congestion region. So that's why it's frontal stationary. Next, there is something that they call between A and B, suppose. So this they call it as a backward forming shock wave. So again, if you notice, this slope of this line is negative. So that's one way of kind of checking whether it's backward or like forward. So backward because the cues are kind of propagating upstream over time, so in that opposite direction of the flow. And forming refers to the increase of the congested region as more and more vehicles come to this intersection. So this is another type. Then we have 4 more types of shock waves. Then next, between say A and D. So this is the one that we are looking at here, and this they call it as forward recovery shock wave. And this is because this forward means the shock waves again are propagating in the same direction as the traffic flow, and recovery means the decrease of congested portion because more vehicles are now getting dissipated. So similarly, you will get 2 or 3 more shock waves, one between B and C. So I'm referring to this this line. Again, it kinds of denotes something related to backward, right? And this is called as the backward recovery shock wave. Similar kind of definition. The dissipation of Q happens and so on. That's why it's a recovery shock wave. And backward means these shock waves are propagating upstream of this red or the stop point. Then there is something between D and C as well. So I'm looking at this one, and this is called as the forward forming shock wave. So this means that this moves in the same direction of traffic, that you can notice, and at like as this flow state D has almost kind of, this has 0 vehicles here, the propagation of shock wave will create some congestion. So that means that's why they call it as forming. And after this dissipation of Q, this forward forming shock wave is formed between A and C as well. So A and C is here, you can also see this is also a forward forming shock wave. So these many shock waves that are created here in this problem, and then you can also calculate different things from here as well, but the quantitative analysis I'll be discussing sometime later. So does anyone have any doubt in this example? If not, I'll move to the next example. Okay, so probably I'll move to that example. So I'll just quickly add this figure. So here there is another example that I'll be talking about. Here it's related to the lane drop at a bridge. So here, if you notice this figure, I think it's visible. I'll just increase. So this is the lane that we are talking about, and then it has some capacity. After a certain portion, after you travel some distance, at this point there is some bottleneck and the capacity decreases. So that means congestion will typically increase because of this. So again we have to see how many flow states are being created, and then also discuss how many shock waves will be created in this. So you can think of like this could be a 3-lane highway that meets a bridge of capacity 2, like of 2 lanes. So that's why it is called as the lane drop at a bridge. Now this demand pattern can be different during different times of the day. So one of the flow states will exist in this 2 lane, and another kind of flow state will be existing between this in this section where there are 3 lanes. Now what happens is that when demand is kind of equals to the capacity of the bridge, so there will be one shock wave that will be formed, which is called as the frontal stationary shock wave. So here this is at this upstream side of it, and it's stationary because, as I have mentioned before, so stationary means the location of that shockwave is fixed. Here it will form. So that's one of the shockwave. So let me quickly write it down. Okay. So this is one is the forward forming shockwave. So this is the straight line that you can, sorry, forward stationary, made a mistake here. So this is the straight line that you notice here. Then what you will have, what you will see is that then actually I should write it as frontal stationary, not forward. So after that, if the demand exceeds the capacity of the bridge during say the peak hours, so what will happen, queues will start to form and it will propagate backward, and then there will be another flow state that will be created, which you can call it as some flow state C. So here the flow state in the 2 lane was A, in the this lane initially it was B, and then there is, so this between A and B you have this shockwave AB, then this is B, and then you will have another flow state somewhere here which is C, which will tell you again this the Q is getting propagated backwards, so that's why you have this kind of a negative slope line, and that is why it is called as the backward forming shock wave. And then there is another another flow state, it's this one, it's between this C state and between this A state, or you can name it as a different state altogether as well. So that will give you a rear stationary shock wave, and you will have another shock wave which is forward recovery with a positive slope. So actually let me maybe add another figure here that will be clear with those namings. Yeah. Yeah, here you have this symbols written. So between A and B you have this frontal stationary shock wave. Between you can name it as B1 traffic state, in between C you have a backward forming, then in between this you have a rear stationary, and then you have a forward recovery shockwave. And so we'll essentially have, I think, 1, 2, 3, 4 kind of shockwaves in this problem. So let me quickly write it down. You will have a backward forming shockwave, then you will have a reverse stationary, and finally you will have a frontal stationary shockwave. So if I want to explain it more, so it will depend again on the demand versus the capacity of the lane or the bridge that we are looking at. So here, as I mentioned, when the demand exceeds, you have this backward forming one, and after that the demand again reduces to the capacity of the bridge, then again a stationary shockwave will be created at the rear end of the queue, and that is the rear stationary shockwave. And then if the demand reduces further, then the queue again starts to reduce, and the traffic will move again in the forward direction, or whatever the congestion will move forward, and that's why you have a forward recovery shockwave of this line as mentioned here. And frontal stationary have been already mentioned. So yeah, that's all about this example. Next, I think, so we have 6 types of shockwaves in general that we have noticed. I think most of them, like 4 of them, have been covered here, and you will as well as have 2 more. One is, I think, what I have missed is forward forming, yeah, and another is, I think, backward recovery shockwave. Yeah, I think somewhere I've written it wrong. This should be forward, oh sorry, oh I wrote frontal stationary twice, so this should be forward recovery. And yeah, you can as well as have backward recovery shockwaves and also have forward forming shockwaves. So that will give you 6 kind of shockwaves that you can have. So I can go into the explanation of this classification more, but I think should not be too difficult to understand with such this 2 types of examples, and I think both of them have been discussed in the class. So if anyone has any questions related to this, you can ask me now. I'll try to answer. Otherwise, I'll move to the next part, which is the quantitative analysis of the shockwaves. Okay, let's start the discussion on okay, so what we can, let's add a figure and try to explain it. So first let's start with this figure. So here what happens is that generally first what has been discussed is the speed of the shock waves in general. So the definition of shock wave is kind of clear, right? When 2 types of traffic states has a boundary, then that demarcation point denotes the shock wave. Now this demarcation point may move forward or backward or stay at the same place with respect to space and time, that we have seen with respect to different classifications in those example problems. Now the rate at which these boundaries move is referred to the speed of the shock wave. So for example, if you have state A with traffic stream conditions having, say, vehicular speed, density, flow as something, say u, k and q at point A, and you have another set of traffic stream parameters here, and those speed densities and flow are different here. Now the speed at which this boundary moves, this is called as the shockwave speed, which is omega AB, and here the flows and this speeds are shown at two different portions in the traffic stream. So now our goal is to calculate this omega AB and the speed of the vehicles in, say, flow condition B here. So you can notice this figure as well. So here this is KA. At this point, this is the traffic stream condition here at A, and at point B you have another density KB, and the flow is also different. This is the Q versus K diagram. Now the way you calculate the speed of this shockwave is that speed of vehicles, you first find out the speed of vehicles in flow condition A relative to the shockwave speed, which will be this UA minus omega AB, and in the other portion you will have a relative speed of UB minus omega AB. Then using that you can just calculate the flow. So you just multiply those speeds by density, and then you can multiply it with time to get the number of vehicles. Now the number of vehicles entering the flow condition 1 will be equal to the number of vehicles that leaves the flow condition B. You can think of it that way, and once you equate those both number of vehicles, you will get a condition which will give you the omega AB value, which is QA minus QB divided by KA minus KB. So if I write it down, the proof has been, I think, shown in the class. So let me write it down. Although yeah, it will take some time to write omega, so I'll just write the symbol. I'm not writing the symbol, I'll just write it like this: omega AB. This is equals to, so we'll have QA minus QB divided by KA minus KB. And the proof is done in the class, and I have already mentioned how to approach this. So you can just join these two lines, and the slope of the line will kind of tell you the speed of the shockwave. And if the slope is positive, then you know that this is a forward moving shockwave. So generally what happens is that, so let me quickly write down forward moving shockwave. Is when a stream of lower flow, so stream of lower flow, which is this QB point you can think of, and lower density, this is again low KB, you can think of this point, meets a stream with higher flow, which is Q is having a higher value here at point A, and higher density. So that's when there is a forward moving shockwave that has been created. Then a stationary shockwave will be created if this line is a horizontal line. So let me so I'll add another figure. Let's this one. So here the slope of the line is 0, or you can have another point C which gives you a slope of the line as negative. So there are two other kinds of shock waves. One is the stationary shock wave. So which tells you that when two streams having the same flow value but different densities meet. So here the flows are equal, QA and QB are equal, but the densities KB and KA are different. So here this is a stationary shock wave, and by the looking at the slope of the line you can tell if it is 0, it's a stationary shock wave. Then you have backward moving shock wave. So this happens when a stream with higher flow, so this is the point QB, and lower density, because you will just with respect to point C you are looking, and lower density meets another stream with lower flow and higher density. So if you look at the picture it will be clear. So you don't have to remember all those things, just look at the picture and just construct these lines and you will know the answer. Okay, so before I go into the examples and mathematics, like the problems, anyone has any doubts here? Okay, yeah, so maybe I can now start looking at some of the assignment problems quickly. Let me check if something is relevant to this topic. Okay, so I think one of the I think first two problems are kind of related. Even first three, yeah, these I have discussed, so let's quickly discuss some of those problems. So let's look at problem 1. So it tells you, so state true or false. So let's look at the first one. So total 6 shock waves are created at a signalized intersection. This we have already discussed and this is obviously true. Then you can have, does anyone has a question? Yeah, forward forming shock wave is created when the demand is equal to the flow of the congested region. Is it true or is it false? So you can look at this example. Here I had already discussed, when demand is equal to the capacity, a forward forming shock wave, is it created or something else is being created here? Okay, obviously the statement won't be true because the congestion won't be moving in this direction where the traffic is moving. In that case, where the demand is exactly equal to the flow in the congested region, it will kind of first form a frontal stationary kind of a bottleneck. So this won't be correct. Let me check if okay, yeah. Next, you can have say backward forming shockwave is created upstream of stop line during red time at signalized intersection. So if you look at this figure, so upstream means, yeah, looking at this, yeah, this is true. Here backward forming shockwave was between A and B, so this one we are talking about. Finally you can have okay, the definition of shockwave. Okay, and I'm not writing it down again. Let's look at another one. Backward moving shockwaves will occur when a stream of higher density and higher flow meets with a stream of lower density and lower flow. Is it true or false? We just had the discussion on this. You can look at this figure. So we're looking at backward moving ones, but in the example what have been told is that higher density and higher flow means lower density and lower flow. Okay, let me, yeah, so here what happens is this, they are talking about this one, but this is not a backward moving shockwave, so this will obviously be false. Then stationary shockwaves are created. Yeah, if no one has a question, can you mute yourself? I think there is some background noise. Okay, I think I'll just mute all. Okay, so it will happen when two stream of same flow but different densities meet, and this is true. We just had the discussion. Then something about the forward moving, okay, shockwave. Let's quickly discuss this. Forward moving shockwaves will occur when a stream with higher flow and lower density meets a stream with lower flow and higher density. So this is higher flow and lower density. Let's look at this figure. Higher flow and lower density, it will be around here, and then lower flow and higher density. So again the slope will be negative in that case, but it is not forward moving shockwave in this case, so this will be false. So anyone has any doubt with all this true false? Then if not, I'll move to the next problem. Okay, so it is related to the speed of the shock waves, and also uh, something related to the number of vehicles in the platoon. So it's, I think the problem is related to the signalized intersection, if I'm not wrong, or let me quickly check. Okay, so let's maybe go back and discuss something related to the theory, and then I'll just explain the problem. Yeah, let's quickly discuss the other topic. Let's look at this example now. So this we have already seen. Yeah, sorry, does anyone have a question? Okay, you can ask me, unmute and ask me if you have any doubts. Okay, let's actually look at this figure. Okay, let me delete this. Sorry. Trying to delete it. Okay. And then let's insert another figure, something related to this. So the first example is very similar. We have already discussed it. So this is the red time, and okay, and also then you have the signal turning green, and then you again have the red time, and based on this you can have some problems, and you have already known that you have 6 shock waves being created here. So I'm not going into the derivation of this has been discussed in the class. If any question comes up, I think you can directly use the formula and get the answer. But let's look at the other example where there is something related to this temporary speed reduction at a section of highway, and this is the right hand side, this figure, where you have this section of highway, and then you have on ramp and off ramps. So from here a heavy truck might enter this 2-lane highway that you have, and initially the traffic stream was having a very high speed, but once this truck enters here, it enters with a low speed, and then the other vehicles that are behind this truck, it is also stuck behind this slow moving truck here, and after some time this truck exits from this off ramp, and then traffic state kind of returns after a certain point of time. So here the flow states that you will have, initially you have this flow state A where there is uninterrupted traffic that was being moving at that speed. Now once this truck enters at this location, you have some obstruction, and behind this truck there are some queuing that is happening, but the truck is moving, unlike the previous example where there is this stops line here, but here this kind of bottleneck or the truck, it is also moving. So that's why you kind of have this between A and another traffic state that have been created, B, you have this forward moving kind of a shock wave that is created. The shock wave is moving in the same direction as the traffic. Then what happens after a certain point, the truck, so at this downstream, you will have no vehicles that can go through. So in front of the truck, there won't be any vehicles as such. So that's why it's a zero flow region that have been created. And then you will also have another traffic state C that have been created. Once this truck exits, it doesn't return immediately back to the traffic state A with those speed, but after some time the queued up vehicles gets cleared, and then the traffic state returns to the original state, which is the state A. So now there can be questions related to how much time it took to clear the queues and so on. So these are marked here, this T1, T2 and T3, that will give you some sort of an indication. So T1 is where the truck enters the highway and with a reduced speed, and then at T2 here the truck leaves the highway, and T3 is still the point where the congestion still remains. Now this shockwave speed, the between this traffic states, you can again calculate using the flow and density values of this traffic states that have been given here. And so the critical thing related to it, I think, will be the types of shockwaves that are created. Those kind of questions you may get, or you can get some sort of a numerical here. So let me see if there was anything that was discussed in the class. Okay, yeah, there were one that was discussed, I think, and in the assignment also probably you have one question related to this. Anyway, let me open another slide. So here I'll just add this figure. So in this again, case. Now, as mentioned in the previous slide, so the number of traffic states that are present here is 4, and again similar to the signalized intersection, you will have 6 shock waves being created, and those 6 shock waves are denoted here. So now you can have data related to, say, shock wave 1. You can have the flow, density, speed values for for this traffic state, say A or whatever was marked in the previous figure. And then if I ask you to calculate the speed of the shock wave, it's just very simple, QB minus QA divided by KB minus KA. Then you may be asked about this starting point of the platoon, or the starting point of the platoon dissipating shock waves. So those you can also calculate. So this point P is the starting point of the platoon, and this point Q is where the platoon gets dissipated. And finally, you might be asked about the ending points of the platoon forming and dissipating shock waves. So then you have to check where the shock waves kind of meet. So it's this point that they are talking about. And you can also calculate the maximum length of the platoon depending on the speed and time, and then you can calculate the flows and the number of vehicles and so on. So let me see what was the question in the assignment. Yeah, so let me write it down in the next slide and solve it. So this is say problem 2. So this tells you again some two-lane undivided highway, and the traffic volume is given. So this is equals to say 2000 vehicles per hour. Then there is this truck that is entering into that highway, but before that you are given the density value as well. So this density is 25 vehicles per kilometers. Then as I mentioned, the truck enters the traffic stream and travels, so truck speed equals 10 kilometer per hour. And then the truck travels for a length of 2.5 kilometers before it goes through that off ramp. Now let's calculate the speed of the traffic, the original traffic stream. So the speed, it's nothing but this flow by density, which is 2000 by 25, and that gives you I think 80, is it? So this is 80 kilometers per hour, and you can see that truck speed is relatively like it's considerably slower than the original traffic stream that were there, and the platoon is formed because of that. So the platoon density is given as 100 vehicles per kilometers, and the flow rate is also given. Because of this, the flow rate becomes 1000 vehicle per hours. So now you are asked about the speed of the shock wave. Find the speed of the shock wave generated because of the entering of the truck in the traffic stream. So how would you approach this problem? So you can notice that the traffic stream that was originally there, we're having this flow as this and density as 25. Later the flow becomes, in the platoon, becomes 1000. Sorry, it is, yeah, the flow is 1000, density is 100, and the initial density was 25. So yeah, so you have all the information. It's very simple. So your omega is nothing but say qa minus qb divided by ka minus kb. So your a was the initial traffic state, this is 2000, later it became 1000, and this divided by ka was 25, and this minus 100. So this gives you this much kilometer per hour, and this will give you 1000 by 75, which is around I think 13.33, but with a negative sign. The sign indicates it's a backward moving shock wave. So you can have this kind of a simple problem that you can solve. Now it may also be asked about the number of vehicles in the platoon by the time the truck leaves the highway. So the truck leaves, let's see this figure. This is the point where the truck leaves the highway T2. So at that point you may be asked to calculate the number of vehicles that are there in the platoon. So let's start a new slide. Okay, the data remains the same, and you are asked now, so find the number of vehicles in the platoon by the time truck leaves the highway. So here what happens is that first you have to find the rate at which the platoon grows with respect to the shock wave. So you know the shock wave speed, so that omega AB or whatever, omega is say 13 point, or it was minus 13.33 kilometer per hour. Then you have the platoon speed you have to find out. So that's again similar, flow rate by density, which gives you 10, which is also the truck speed. So platoon will grow at a rate, so this is 10 minus of minus 13.33, so it will be plus, so that gives you 23.33 kilometer per hour. Now the length at which for which the truck travels is 2.5 kilometers and the speed is 10. So you know the time till which the truck was present. So truck will spend 25 by, sorry, not 25, 2.5 by 10. That much amount of time equals 0.25 hours in the traffic stream. So it's now simple. You can calculate, you have the speed at which the platoon grows and the time till which the truck was there in the platoon. So you can calculate the length of the platoon. So length of the platoon is easy. You can just multiply those two. It's 23.33 times 0.25 kilometers, and that gives you, I think, 5.83 kilometers, around that. And finally, what you can have is you have to find the number of vehicles in the platoon, and you have the length of the platoon, you know the density, and you can just multiply those two and get the number of vehicles. So number of vehicles in the platoon is 5.83, this is the length, and the density is 100 vehicles per km. So this becomes 583 vehicles. So that's how you solve such problems. So anyone has any doubt related to this? Otherwise I'll move to another discussion. Okay, so if not, I'll probably have some discussion on the remaining portions of this shock wave and then move to queuing. Okay, so shock wave propagation, I think the green shields model and everything was discussed in the class, but as such in the assignments I think I didn't find many questions related to that. So I think you can go through those, and now let's, I think, move to queuing. Okay, so I'll start a new slide. Okay, so what do you mean by queuing? So if I ask you what what is actually queuing and how does it kind of forms or happens? Okay, so maybe let me write down some of the key points. It's congestion, or let me write it as traffic congestion that leads to queuing. So now it can happen because of on ramps, off ramps, signalized intersection, signalized and unsignalized intersections, and so on. It might be like time dependent as well, not only space. Like in peak periods, you may be having considerable amount of delay. So delays during peak periods. So now if we look at it, so it's some terms that have been defined in the class. One is traffic demand. So this is related to how many vehicles are willing to pass a point on the road in say 1 hour. So the unit is vehicles per hour. So this is number of vehicles desires to pass a point in the road in an hour. Then you have observed traffic volume. This is different from the demand because this is actually what you count. So this is the number of vehicles that actually passes a point on the road in an hour. And finally you have the traffic capacity. So this is in vehicles per hour again, and you know already the definition. So the maximum volume that a particular point or segment of a facility can accommodate. Okay, so now there are some relations. So if the traffic demand is less than the capacity, then observed volume is obviously will be equal to the traffic demand. Now if the traffic demand is greater than the capacity, observed volume on the road will be less than the actual demand, and there are some challenges in measuring that. So when that happens, we know that congestion is present, so drivers might switch to alternate routes or may travel at a different time during the day. He or she might even cancel the trip. So all those effects will be there, and there will be some part that can be measured and some part that you won't be able to measure. Now there are some techniques like volume in alternate routes and all those things you might measure, but the trips that do not occur due to congestion, you won't be typically able to measure. So there is something about these measurements and all. Let's move on to the next is demand, volume and capacity and their relation. And there was one example discussed in the class related to this, and also same, I think similar discussion was also done. Like there is one problem related to this in the assignment. So let me check. Okay, so let's discuss this problem. So this is on relationship between traffic demand, volume and capacity. Okay, and let me add a figure. So the one that is important here is this one. So here in this figure, so this example was discussed in the class. So what happens is that the demand is varying. So in the first 30 minutes, the demand was 50. This is in vehicles per minute. And then from 30 to 90 minutes, the demand was 120 vehicles per minute. And from 90 minutes onwards, your demand was 65 vehicles per minute. But your capacity, which is shown by the red line, was 75 vehicles per minute, which is constant throughout. Now for this portion, actual volume that you will measure, observed volume, will be equal to 50, which is the demand. But then after that you will have this excess demand, and so based on that you will have some Q that will be formed, and there are questions related to this, I think, in the class. So let's quickly mention that. So one is the what would be the Q length during this period when demand exceeds capacity. So demand exceeds capacity. So here the Q length will be whatever the excess demand you have during this period, and that will give you, so it's 120 minus 75. This is the excess demand in vehicles per minute, and this is happening for 60 minutes, which is 90 minus 30, and this gives you, I think, 2700, 95, 45, yeah, this many vehicles. So this will be the Q length for that. And now how long will this Q take to dissipate after 90 minutes? Okay, how long will Q take to dissipate after 90 minutes? So if I ask you, so the answer would be, so whatever that is passed, so this 75 minus 65, this is the extra, so this 10 vehicles per minute, and then you have 2700 vehicles that needs to be passed. So if you do this, you will get 270 minutes. So this was a simple example that was discussed. Then you may be asked about, at this location, what is the observed volume with respect to time. So let's maybe answer this. Observed volume, so between, say, 0 to 30 minutes, it is, it was 50 vehicles per minute, and this is for 30 minutes. So this is 1500 vehicles. Then you have between, say, 30 to 90 minutes. So for those 60 minutes, the observed volume was 75 times 60, which gives you, I think, 4500 vehicles. And finally, for the rest of the time beyond 90, so I think in the class it was taken till 6 hours, so 90 to 360 minutes. So that will be because so this queued vehicles took 270 minutes to pass, so that's why it's taking 270 minutes from that point onwards. And it was again in capacity as well, so this will be 75, which is vehicles per minute. And if you multiply it with this 360 minus 90, which is 75 times 270 vehicles. Okay, so it would be around 75 times 270 is 20250 vehicles. Okay, so I think a similar problem was there in the assignment, so let me quickly check that. What was the problem? Okay, yeah, so there was slightly different curve that was there in the assignment. Okay, let me delete this and let's look at the assignment problem. So in the assignment you have this figure. So if you look at this figure, what you have is 1500 is the capacity. Here it is denoted by green, and this is the demand till 1 hour. Then you have a different demand from 1 to 1.5 hours, then it remains again constant, then it drops to this point, again drops and remains constant. So you have a 6 hour of data. Now if I ask you, so this is determine the length of the queue dissipated at t equals to 3.5 hours. So this is the first question. Now how would you answer this? So till 3.5 hours, so here there is some decrease that is happening. Here there was an excess demand and those you have to pass through as well. So demand rate is decreasing. Here it was 1800 at 2 hours and 1000 at 3.5 hours. Sorry, this was at 2.5, this is at 3.5. So in 1 hour the decrease were 800 vehicles. So here, and right, demand rate is decreasing at a rate of, so that's 1800 minus 1000 divided by 3.5 minus 2.5, that is I think 800 vehicles per hour. Now this time taken to decrease of demand flow rate from 1800 to 1500, so this till this point you can check, so that will give you the intermediate point. So let's check time taken to decrease. So essentially we're finding out this red point where this time kind of meets. So time taken to decrease of demand flow rate from 1800 to 1500 vehicles per hour is, so the decrease is 300 and the rate was 800 vehicles per hour, so this will give you this much hours. So this is 0.375 hour. So at 2.5 plus 0.375, which is 2.875 hours, the demand rate will reach the capacity. So till now we have just found this point. Now we have to find the length of the queue that was dissipated. So time till 3.5 hours to dissipate the Q. So this is the time for which Q is dissipated. So from 2.875 to 3.5. So it's just the difference that you have to take. Sorry, this is 2.875. So that's 0.625 hours. So this is the amount of time in which the Q is getting dissipated. Now the length of the Q you have to find out, and that you can do using this probably let me check. Okay, is there any information that's missing? Okay. Okay, so you can just find the area of the triangle that will be created if you draw a vertical line from here, and if you take the area of the triangle, that will give you the number of vehicles in the queue. So length of the queue dissipated, that would be half times this vertical distance, which is 500, 1500 minus 1000, and then you have the horizontal distance, which is 3.5 minus 2.875, that I have already calculated. So this will give you the length of the queue in kilometers. Sorry, it's vehicles. So it will be let me calculate it. This is 0.5 times 500. This is 0.625. Okay, so it's 156.25 vehicles, or you can round it up to 156 as well. Okay, so then you may be asked about, let's try another problem with a different, same data, different problem. Determine the size of Q developing during the period when demand is greater than capacity. So again, it's very similar. So it's this portion, this area of this portion that you have to find out. So it is this triangles, area of this triangles, and then you have the area of the rectangle, or you can directly get the area of this trapezium as well, but for that you need to have this data where this intersects, this red line intersects with the green lines. So in the similar approach we'll solve this. So demand rate is increasing between 1 and 1.5 hours. So increasing at a rate equals 1800 minus 1200 divided by 1.5 minus 1. So this is 1200 vehicles per hour. Then you have to find this point where this intersection happens, and this increment is 300 until this portion, and the time is time taken to increase the flow rate from 1200 to 1500 is equals to, the increment is 300 divided by the flow rate, and it gives you 0.25 hours. So this is basically 1.75 hours. Then you have to find this one you have already got from the previous question, and that was 2.875. So the length of the queue is again the area of the trapezium, so length of the queue, and the formula is 0.5 times the length of this parallel lines, and this parallel lines are, this one is between 2.5 and 1.5, so that's 1 plus this is 2.875, and this is 1 point minus what was this, 1.25, and then you have this distance which is 300. So this gives you this many vehicles will be your final answer, which gives you, let me calculate. So it's 1 plus 2.875 minus 1.25 times 300. It's 0.5. Okay, so it gives you 393.75 vehicles. So this was again simple problem. Now in the assignment, what was left is, okay, I think some discussion on signals, I think that's remaining. Let me quickly check what was left in the class. So till this point, does anyone have any doubts related to this? You can ask me now. Okay, so next, I think in queuing analysis, if I go back to the class material, so let's look at another example problem, this one. So here I'm not going to solve the problem as such, but let's look at the concept here. So here what you have is this merge points. So this is approach 1 and approach 2, and they are getting merged together here. Now in approach 1 you have the capacity as 4000 vehicles per hour. Your demand is lesser than that, so it can accommodate all those demand, and the observed volume will be equal to the demand. Similarly, in approach 2, the capacity is 4000 and demand is lesser, 3600, and the observed volume will be exactly the same, so it can accommodate those demand. But once you merge here, your capacity is not exactly like 4000 plus 4000, it's not like 8000, it's something less, which is 6000, and the number of vehicles that are intending to enter this approach, this merged point, is 3600 plus 3800, which is 7400, and the volume, the observed volume, will be equal to the capacity in this case, because it cannot accommodate for the excess demand. So that's why, so some queue will be formed here. So this queue will start at the merge point and propagates upstream, and it is at the rate of 1400 vehicles per hour, which is the difference between this demand and the observed volume. Now what you can have, you can like identify some bottleneck at certain sections. So I think it was discussed in the class, the bottleneck could be, depends on how many like on ramps or off ramps you have, so not necessarily related to this example. So I think another example probably was discussed in the class. Okay, no, this one, let me check. Yeah, so I think yeah, another problem was discussed. A section of highway having two on ramp and two off ramps, and there was certain interesting things that came up. There were total kind of five different sections that were present, and then the job was to identify the bottleneck link, or the portion of the highway that was having the bottleneck. And it was noticed that once you identify a bottleneck, it might happen that you are facing with another bottleneck, so another section might also be having the bottleneck. So the bottleneck location is not like kind of fixed, but you also have some hidden bottlenecks as well. So maybe I'll just add another figure and explain it. Okay, so here you have, yeah, this is the one that I'm talking about. And yeah, in this example, so this is the traffic stream, it's moving in this direction. You have two on ramps, and then you have two off ramps, and you have this section S1, S2, S3, S4 and S5. Both this section have some demand associated with it and some capacity, and based on that, the portion where the demand exceeds the capacity, it is identified as the bottleneck. In the example in the class, I think the section 3 was a bottleneck, but once you have excess demand, your actual observed volume will be equal to the capacity, and maybe later in this portion you won't be seeing any bottleneck, but once you remove this bottleneck, more vehicles probably can enter here, and in that case this can also have some bottlenecks. So you have to identify those things, and I think one example was worked out in the class, and yeah, I'm not going into that example right now because it will take a lot of time, but in general, if you have doubts, you can ask me right now. Otherwise, I'll look at a different problem. So this is, I think, fine. In the final, I think, lecture, only, yeah, deterministic and stochastic this queuing was discussed. Yeah. Yeah, anyone has any doubt, you can ask. Otherwise, I'll look at the remaining problems in the assignment. Okay, let's look at one problem related to signals. So let me open the question and it will be clear. Okay. Okay, now we'll look at again at signalized intersection and some queuing analysis. Okay. So let me look at this. So this is the problem data that are given to you. So the problem kind of checks for this single lane approach to a signalized intersection where your effective green and red times are given. So this is where the green phase begins, and then it stays till the 60 seconds. So your effective green time is 60 seconds, and then you will have again this horizontal portion that gives you the effective red time, which is again 30 seconds. The arrival rate of vehicles on this approach is also given, and saturation flow rate is also given, and then you have to assume that at t equals to 0 the signal was turned red, and then you have to find the average delay for the arriving vehicles within one complete cycle. So that one complete cycle, I think, stays still this 60 seconds. So let me write down the data. So the data for this problem is effective green time, which is 30 seconds. Then you have effective red time, which is 30 seconds, and arrival rate of vehicles, it's 360 vehicles per hour. And then you have saturation flow rate, which is 1400 vehicles per hour per green time. Okay, it's written as, okay, let's calculate the average delay for the arriving vehicles within one complete cycle. Okay, so you can look at this portion. This is one cycle till 60 seconds, or you can look at the other portion as well, from 60 to 120 seconds. It's the same kind of plot. It repeats. So this is the cycle length is 60 seconds here, and what you are asked to find is that what's the average delay within this arrival vehicles within the 60-second cycle length. Now for this, what you have to check first is that the arrival rate of vehicles are given, which is 360 vehicles per hour. So from here you can calculate the number of arrivals within a cycle, which is within 1 minute, and that would be 360 by 60 minutes, which is 6. So let me write down in the next slide. So the data was given in the previous slide here. Number of vehicles arriving in a cycle. So this is comes out to be the data was arrival rate is 360 vehicles per hour, and you have to check for 1 minute or 60 seconds. 60 divided by 60, so this is 6 vehicles. Okay, now what you have to find is this, because so in the y-axis what you have is the cumulative arrival or departure, and if you calculate the area of this triangle, that will kind of give you the what you call is the vehicle seconds. So in this x-axis you have seconds, and in the y-axis you have it, and once you calculate it, you can divide it with the number of vehicles arriving in a cycle, and that will give you the average delay. So in order to calculate the area of this triangle, what you have to find is where this point ends, right? So area is typically would be half times this distance times this height that are present here. So basically you have to get this height, which you have to find, I think, through saturation headway probably. Let me quickly check. 400 vehicles per hour. Okay. Yeah. So saturation headway is given as 1400 vehicles per hour. Now within in 1 minute you can okay, so this is 360. 360 is the arrival rate. Arrival rate is 360 vehicles per hour. So arrival rate is lesser than the saturation flow rate, so that's not a problem. So this is 30, this is half, and you have to find this one. Okay, so you have 6 vehicles driving in a cycle. Um, 60. Okay, let me quickly check what was done in the class. I think I am missing something. Okay, so you have to find the number of vehicles that are queued. So, and then you can find the average delay. So there is a formula which is RTQ divided by 2C, that will give you average individual delay. Okay, so TQ is the horizontal projection of the queuing triangle. So that's mu r divided by mu minus lambda. So that's okay. So so it's lambda, which is not written clearly in the lectures. Yeah, lambda is the arrival rate, which is 360. Then you have C, and then okay. C is the cycle length. Okay, so this part is not very clear from the lectures also, I guess. What is C? Okay, so you have to find the number of vehicles arriving within a cycle. So number of vehicles per cycle, which is I think lambda C by 3600. So your lambda is the arrival rate times the cycle length, which is 60 seconds. So this will give you this gives you 60 by okay 10, which is 6 number of vehicles per cycle. Okay, sorry, I have to calculate number of vehicles cubed, which is lambda tq by 3600. Lambda is given, r is the red time, and mu is the mu is the total capacity. Okay, so let's do it this way. So time duration of Q. So this is nothing but mu r, which is it should be mu r is the red time, which is 30 seconds divided by mu minus lambda. So this much seconds, and then we have to multiply it with lambda. Let me just get my calculator. So it's 1080. So it becomes 40 seconds, and then you have your lambda TQ, number of vehicles queued, which is lambda is your arrival rate 360 times 40 seconds divided by 3600. So this gives you um, 360 vehicles per hour. So this you convert it into hours. So this many vehicles. So that becomes 4 vehicles. Now you get the number of vehicles queued, which is what we were intending to find, is this height that I talked about earlier, and then it's just finding the area of the triangle. So if I'm asking you to calculate the average delay of the arriving vehicles, so it would be average delay 0.5 times 30. Let me just check if I'm doing it correct. So 0. Half into 30 into 4, this gives you the total delay of all the arriving vehicles. If you divide it by 6, you will get the average delay. So that will be 60 by 6, which is 10 seconds. So this will be your answer. Yeah, it took a while to solve it, but yeah, it was kind of confusing from the lecture, but anyway, this is there. Hopefully you will be able to follow it. Just go through the lectures once. Just use the formulas that are written there, and you can calculate it for any problem. So we're almost close to 9 p.m. So the rest of the problem were, I think, again related to this accept reject statements. So again, something meets with the bridge with capacity 2 lanes. Okay, this is discussed already. Traffic demand and observed traffic volume in absence of congestion. Okay, this is also discussed. Demand starvation and hidden bottlenecks is also part of the discussion in the queuing, which is, I didn't discuss it fully, but it's present in the slides. I think you can go through it. There are not many, I think, problems or questions related to the other portion, which is the stochastic queuing. So I guess I won't be going through those discussions for now, but later if we have time in other classes, we might discuss those as well. So yeah, I'll probably stop today's discussion. So do you have any questions? You can ask me now. Otherwise, I'll stop and continue next week. I'll share the slides and also upload the videos as well. It will be uploaded, I think, tonight or maybe tomorrow, by tomorrow morning. Yeah. Okay, so if you don't have any questions, you can leave the meeting. I'll continue the discussion next week. And yeah, and if you have doubts, you can always post it in the discussion forum. Okay, thanks. Okay, I'll close the session. See you all next week.